The application of steel in low-temperature thermal desalination. Water scarcity is a global issue that affects 1.2 billion people, a sixth of the world's population. Another 1.6 billion people are affected by a lack of resources that prohibit them from acquiring water from rivers and other water sources. Along with the changes that will occur to the Earth due to climate change, it is estimated that water scarcity will affect all parts of the world in the near future. It is evident that fresh water is a scarce resource, and with the rapid growth of the world's population, it is becoming far more pertinent to investigate a solution to this problem. Water is plentiful on Earth as it covers 70% of our planet, but of this 70%, only 3% is fresh water. Of this 3%, two-thirds is unavailable for use as it is found in frozen glaciers and other places. One of our group members is from Virginia Beach, and another is from Atlanta, Georgia. These areas have experienced major freshwater shortages in recent years due to nutrient dumping in the Chesapeake Bay and overuse of water by southern Georgia farms. These problems have led to political wars with Alabama and Florida over water access rights and major pollution around the state of Virginia. We have seen these issues manifested in witnessing pollution and Georgia lakes dropping in up to 20 feet in depth. We are not removed from the major water issues, and if nothing is done about it soon, no one will be. It appears that an obvious solution to this problem would be to use the abundance of salt water that is present on Earth. Desalination is a process by which fresh water is rendered from salt water by separating salt from ocean water. Ancient techniques have been adapted to produce more efficient processes, as in to produce more fresh water and use less energy. Low-temperature thermal desalination pumps salt water into large evaporation tanks made of steel. After the salt water has been evaporated, salt has been separated from the water. Then the water vapor can be cooled back down and be completely free of salt. Low-temperature thermal desalination also can be maintained using renewable energy, and thus is the most creative and promising method of desalination to emerge in the last 20 years. Carbon steel used to make up a large portion of the low-temperature thermal desalination plant, the evaporation phase in particular. It was readily available and an already well-known material, which made it easy to use. However, carbon steel was also known to corrode quickly. The corrosion and rusting of the carbon steel mainly occurred because of the nature of its function. The presence of oxygen, carbon dioxide, chloramine, and the heat in the salt water evaporation process led to that would then initiate corrosion cracking of the carbon steel. Thus, this material was not an effective material, had to be replaced, and needed a substitute that could better resist corrosion. Enter stainless steel. Stainless steel is less corrosive than carbon steel, allowing less to be used, decreasing the weight of the plant, and decreasing the necessary maintenance. In most steels, the iron atoms are oxidized in the presence of oxides, but the increased amount of chromium present in stainless steels causes the chromium to be oxidized instead, which causes a layer of chromium oxide to form and greatly lower the diffusion rates of additional oxide. However, stainless steel is still corrosive. Carbon steel thins, but stainless steel pits, which means that it corrodes in localized areas. The transformation of using carbon steel to using stainless steel in the low-temperature thermal desalination process increased the life of the average plant by 15 years. That time used to be needed to maintain the plants can now be used to increase desalination of more water. This caused greater efficiency of the process, and using thinner lining of stainless steel dropped the weight and cost of the plants. The money saved with this implementation could be used to improve the other parts of the process and can mean fewer risks are involved in the investment in more plants. In low-temperature thermal desalination plants, the stainless steel alloys that make up the evaporation plant's tanks are exposed to high chlorine ion concentration due to salt water, which can interfere with the stainless steel's ability to form a fully protective film. Tiny local fluctuations will degrade the oxide film in a few critical points called pits, where corrosion usually takes place in stainless steel. Corrosion will be greatly amplified at these pits, and in extreme cases, the sharp tips of extremely long and narrow corrosion pits can cause stress concentration to the point where the stainless steel can shatter. These problems are especially dangerous because they are difficult to detect before a structure fails, which shows that the fatigue failure is a large risk for stainless steel under these salty conditions. The material science and engineering triangle shows the relationship between processing, structure, and properties of a given material. All of these aspects of a material affect each other, since, for example, desired properties you may need require certain structure, which requires a certain process. For our project dealing with the use of different types of steel in the evaporation phase of low-temperature thermal desalination, we can apply the MSC triangle and what we have learned about fractures and fatigue to better understand how the use of duplex steel can make for a more efficient and cost-effective process. Almost all plants use stainless steel as a material for their evaporation tanks. The desired structure is a steel with relatively large amounts of chromium present, which means many stainless steel components must be exposed to mechanical loads in the processing stage. But what comes along with this is a process that creates high strains inside the material and a structure with grain boundaries that are more sensitive to corrosion, which will impede the entire process. We can now see how high strain levels in certain areas could be problematic from what we know about fractures and fatigue. As corrosion increases, cracks will grow at stress concentrations. If the crack length reaches a critical size, the steel will fall victim to fatigue failure. To avoid complete failure of stainless steel, parts of the evaporation system would have to be regularly replaced or repaired, costing time and money. Perhaps there is an alternative to stainless steel that avoids the issue of stress corrosion cracking. Now enter duplex stainless steel. This steel offers excellent resistance to corrosion and has a very high mechanical strength. The high corrosion resistance of duplex stainless steels ensures significantly more uptime than carbon steels and conventional stainless steels, while the mechanical strength allows for lighter constructions, more compact system design, and less welding. Duplex stainless steels have a mixed microstructure of austenite and ferrite. The aim is usually to produce a 50-50 mix, although the commercial alloys of the ratio may be 40-60. Adding chromium allows ferrite and austenite to create a steel alloy that can be used in the evaporation phase. With these superior characteristics, duplex steel can be used to apply in the desalination plants to produce a thinner evaporation shell wall that has also required a higher resistance to corrosion and erosion, which will lead to more efficient evaporation tanks. During the formation of stainless steel, sulfide molecules attract chromium atoms, which creates a dearth in chromium concentration surrounding the sulfide. This creates concentration disparities that are the sites for the steel corrosion cracking. Ridding the steel of sulfide would mitigate corrosion, but would also make it harder to mold the steel into the desired shape and structure. This is where the use of duplex steel as a replacement comes in. The processing of this material can be changed to allow redistribution of chromium atoms around sulfide atoms by speeding up the cooling process. Doing this would prevent the chromium atoms from diffusing toward the sulfide and would allow the chromium atoms to more evenly distribute through the material. This would allow a decrease in the tendency for carbon separation or corrosion, and would make possible the same evaporator structure that stainless steel makes possible without the risk of corrosion, fractures, or fatigue. Thus, using this new steel could result in a 30-40% savings on equipment over the life of the system, meaning more plants could be built and serve as a step in the right direction to solving Earth's freshwater scarcity crisis.